Welcome everyone, my name is Eugenio Pescimora and I'm a PhD student in Applied Mathematics at the University of Nottingham. This presentation is the result of a collaborative work whose main contribution come from, but are not limited to, my supervisor and the collaborators from the Engineering and Maths Department of the University of Nottingham and the British Geological Survey. So, in this short talk, I will outline the main capabilities of our open source OpenFOAM library available at the link in the slide. While the library is currently under active development, a first version has already been released within the Secure project, and a new extended version will be available soon. This tool is designed to ease the simulation and analysis of solid transport in porous media. The pre-processing utility setRandomField provides a wide range of choice in the selection of the porous media heterogeneities, such as continuous, truncated, or pluritruncated Gaussian random fields. On the right, you can see an example of a pluri-Gaussian simulation field generated in collaboration with Aphasia. The flow and transport part relies on classical OpenFOAM partial differential equation solver capabilities in a new Eulerian framework. A great advantage of using OpenFOAM library is that all our solvers and utilities come fully parallelized out of the box. The main objective behind the implementation of this toolbox are to integrate geostatistics, flow, and complex transport processes and post-processing, which links to the objective of my PhD, which is to study the limitation of Fickian transport models in capturing anomalous solute behavior, which arises in highly heterogeneous media. We have decided to base our toolbox on the C++ OpenFOAM library. Indeed, apart from its open source nature and wide development community, some of the key features of OpenFOAM we like are its C++ object-oriented structure, which allowed us to reuse many features such as adaptive time stepping, complex mesh generation, and Picard iteration. The solvers and utilities I will talk in this presentation are simple Darcy foam, an extended version of scalar transport foam for adaptive advection dispersion equation in porous media, and the geostatistics utility setRandomField. For visualization of the results, we rely on ParaView, a powerful graphical user interface for data visualization. So let's see the main feature and capabilities related to setRandomField utility. One of the driving factors that controls the onset of non-Fickian behavior is the heterogeneity contrast of the permeability phases. For this reason, and for the high realism degree, we focused on the implementation of an algorithm that yields non-Gaussian random fields characterized by sharp heterogeneity contrast. However, since the pluri-Gaussian fields rely on a combination of continuous Gaussian fields, the setRandomField dict settings allow for a wide range of geostatistical field type characterization through a selection of several geostatistical metrics such as correlation function, correlation length, mean, and variance. The setRandomField library core is the Fourier decomposition, which is at the base of Gaussian random field generation. A Gaussian random field can be represented using a stochastic Fourier integral, which means that it is possible to use a stochastic process to generate a Gaussian random field in the frequency space. We then apply the inverse Fourier transform to retrieve the spatial random field. The basic idea behind the method is to multiply the spectral representation of a given covariance function and the Fourier transform white noise. The result is a Gaussian random field in the frequency space characterized by a particular covariant function. By means of the inverse Fourier transform, it is possible to retrieve the spatial representation of the Gaussian random field. Random field library offered three main covariances type: Gaussian, exponential, and Matern. We provide the spectral form S of k of these variagrams because of the method we used to implement the random field generation in OpenFOAM. Other variogram and covariances can be implemented simply by adding the random field generation in OpenFOAM. Other variogram covariances can be implemented simply adding their spectral density. This slide shows a couple of continuous Gaussian random field examples. On the left side, we have a Gaussian random field characterized by Gaussian covariance, while on the right, the covariance function of the Gaussian field is exponential. Lambda here is the correlation length. To transform a continuous Gaussian simulation into a truncated Gaussian simulation, we need to establish an interval definition rule, also called the truncation rule. The principle is to simulate one or more than one in the pluri-Gaussian simulation case, a Gaussian variable at every point in the domain, and by means of a binning process, replace the value taken by z of x between two thresholds, ti and ti plus 1, with constants, each of them corresponding to a specific homogeneous body of rock, otherwise called facies. The smooth transition, which characterizes the Gaussian random field, is then replaced by I plus 1 categorical values, and the final result is no longer Gaussian. For example, if we know from field observation that the volumetric proportion of the dark blue faces should be 30.8% and that it should touch just the light blue faces, we can draw a truncation rule like the one in the image. This interval definition is called truncation rule. In this sense, the truncated adjective refers to a Gaussian random field that has been binned. Pluri-Gaussian simulations are generated by taking the values of two Gaussian random fields, Z1 and Z2, at the same spatial position, and using them as coordinates to enter the corresponding truncation rule. The value corresponding to these coordinates in the truncation rule will determine the faces at the same spatial coordinates on the final pluri-Gaussian simulation. We now have an OpenFOAM library called the setRandomField that generates pluri-Gaussian simulation. Thanks to that, it's possible to run flow and transport simulation in realistic heterogeneous porous media. So, transporting porous media at Darcy scale can be typically ascribed to the simultaneous contribution of three main physical mechanisms: molecular diffusion, advection, and mechanical dispersion. Considering the classical continuity equation and substituting the concentration C to the density ρ and the flux per unit area J to the Darcy flux ρV, we obtain the advection dispersion equation for the case of no source sink terms within the domain. By including this simple mechanism with constant dispersion in our model, we enable the study of the effect which heterogeneous velocity fields have on transport. In addition to this, the secure foam library also implements more complex dispersion, dual porosity, and multi-rate mass transfer models. So the solution of the advection dispersion equation requires the velocity field V, which is determined by solving the groundwater flow equation through simple Darcy foam in case of constant density or rho Darcy foam for variable density case. Extension to dual porosity as well as pore mechanics are also implemented but are not discussed here. Picard iterations are implemented within the OpenFOAM pimple or simple loop controls, since the equations are solved in a segregated approach. I want now to present some preliminary results of my PhD, which is focused on the use of this platform to study non-Fickian transport. This video summarizes an example of anomalous transport study. The top left image is a truncated permeability field, while the video on the bottom left visualizes the longitudinal cross-section of an aquifer where a slag of non-reactive tracer is injected through a control volume. A breakthrough curve is extracted and analyzed to understand the onset of non-Fickian transport. Several other tests were conducted by varying several parameters, such as Peclet number, correlation length, correlation function, permeability constant, boundary, and injection condition. These preliminary results show breakthrough curves from a set of three-dimensional transport simulations run on pluri-Gaussian permeability fields. Here are the impulse, response, and cumulative breakthrough curve. We can compare realization with identical geostatistical parameters on the left, where deviation from the exponential trend are caused by stochastic realization, and analyze trends while changing, for example, correlation length on the right. We are currently working on an automatic post-processing tool based on the OpenFOAM function object structures that will enable to study a wide range of metrics, including not only standard things like moments, but information metric as well. And here are some examples my group has been working on, developing a workflow that includes the import of reservoir data, the reconstruction of small-scale heterogeneities through random field generation, the solution of flow field, and the mass transport using a multi-rate mass transfer model. Thank you for your attention, and get in touch if you are also working on OpenFOAM and interested in collaborating.